Happy Friday, everybody. So let's take a quick look at our question today. All right. You're speeding up at a rate of 10 meters per second squared. How would you explain what that means to someone who doesn't know physics? Anybody?
I can try.
Sure, let's hear it.
10 meters per second.
Yeah.
Okay. So you go 10 meters.
Okay.
Every second.
Okay, well, that's what 10 meters per second would be. So you're halfway there.
That's how I would explain it.
Because, yeah, it's easy enough.
A certain distance. 10 something, I don't know if
Right. Because then the square is what makes things confusing.
Yeah, I don't know.
Yeah, because it's easy enough to know what 10 meters is, and we know what 10 meters per second is. It's 10 meters every second. So what could 10 meters per second squared mean? Zach?
Every second you're going 10 meters per second faster.
Exactly. So go ahead and write that down. Every second, you're going 10 meters per second faster than you were the previous second. So each second, you're going 10 meters per second faster than the previous second. So, when we're talking about an acceleration, which is the main topic we'll be looking at today, what we're talking about is how quickly we are gaining speed. So, like in this example, 10 meters per second squared means that after 1 second, you're going at 10 meters per second if you release something from rest. After 2 seconds, you'd be going at 20. After 3 seconds, you'd be going at 30, and so on. And that's what an acceleration represents for those units. For your notes today, go ahead and write down A versus T. Versus T. We're going to be doing acceleration versus time graphs today, and we'll see how that matters. Yep. As you can tell from the board, we're going to be doing things with 3 graphs now instead of 2. So triple the fun. Go ahead and write down and draw these 3 graphs. Our goal today is to get ourselves familiar with acceleration and how it connects with the other 2 graphs that we've made so far. So, just like last time, we want to make sure that we can translate some sort of scenario onto these graphs. And we'll start with kind of a rather simple one. We've done this one in the past already. I'll let you finish drawing. I can see some people are still going. That's just fine. So A obviously stands for acceleration. The units on that are meters per second squared. If you feel like you need to write that down, feel free. Otherwise, we're just going to jump right into this here. So let's say we've got our scenario. Sharky's right here. Origin's right here. And time begins right now. Time stops. So he's moving away from the origin at about a constant speed. So we want to make sure that we can put that information on these three graphs. So, as time goes on our position time graph, the shark's distance from the origin gets bigger and bigger and bigger. So we would have a graph that looks something like this. Anybody remember what the velocity time graph looks like for this scenario? Exactly. It's a straight horizontal line. And will that horizontal line be up here or down there?
Let's start with the origin.
That's true. Yeah. So what do you think? So one thing to remember when we're making our velocity time graphs is that where we actually begin is not going to affect this graph at all. Because this is a graph of velocity time, so it doesn't tell us exactly where we start. What matters, though, is where we're headed. And in this case, we're headed away from the origin, which is the positive direction, which means this is going to be a positive velocity. Is our speed changing for this? No, because the velocity does not change as time goes on. Whatever this value is for velocity stays the same. So if that's true, that means we don't have a situation where we're picking up speed or slowing down. So our acceleration then would just be 0. So that would be one example. Let's do another one. You can draw 3 more graphs. So the next scenario, the shark begins at the origin, and time begins right Now, so he starts off slow, maybe even at rest. And then as time goes on, he picks up speed. So he's accelerating. So then the question is, how is that going to look on these graphs? So let's think about this. As time begins, we start at the origin. So we know we're going to be starting here. And as time goes on, the shark gets further and further away from the origin. So we're going to be heading up this way, but we know that the speed is changing. Now remember that the slope on this graph represents velocity. So if he's picking up speed, what's going to happen to the slope on this graph as time goes on? Yeah, it's going to change. Is it going to go up or down? Yeah. So we start with a really small slope, maybe even a slope of 0 if we started from rest. And as time goes on, that slope grows and grows and grows and grows. So it's just a big curve. So we are picking up speed in the positive direction. For the velocity time graph then, we know we're going to start here at 0 because we are starting from rest. As time goes on, the velocity is going to grow because you can see over here our slope is growing and getting bigger. In the scenario, the shark was picking up speed. So that means our velocity is going to be getting larger and larger as well. You'd be doing that if you had changes in speed that were abrupt. Like if you were at rest for a while and then you started moving quickly. But because it's a gradual thing, our velocity is gradually increasing. So this would be and we've written this once before already. This is a constant acceleration. We are speeding up. In other words, we are accelerating. And we also have a positive acceleration. And again, just because we're speeding up does not necessarily mean we're going to have a positive acceleration, because from the question yesterday, if we're speeding up in the negative direction, that is a negative acceleration. So now the question is, what's the acceleration time graph going to look like here? Good guess. So if you think about our velocity time graph, our velocity is increasing at a constant rate. So if that's true, that means we're going to have ourselves a constant acceleration. So our acceleration time graph is going to look like this. Constant positive acceleration. Yep. Anytime we're drawing an acceleration versus time graph in this class, it's going to be a horizontal line, as you're going to see from the examples that we're going to go through today. Now, if this seemed a little bit abstract to figure out how you're going to get your acceleration time graph here, I've got some good news for you. In the same way that the slope of a position time graph tells us about velocity, the slope of a velocity time graph tells us about acceleration. So you don't even need to know what's going on in the scenario to draw this graph. You just have to know that this is a positive slope. If we have a positive slope here, we're going to have a positive acceleration. If we have a positive slope down here, we will also have a positive acceleration. It's all about the slopes, folks.
So velocity and acceleration always line together.
Will they always line up?
Like if that
Yeah.
makes any sense.
In terms of the slopes?
Yeah.
Yes. Yes. So whether this positive slope is there, or even something like this, or this, these will all give you the same acceleration versus time graph.
And then the acceleration is always horizontal.
Yes, absolutely. So we can take this just one quick step further then before we jump into some examples of this. So just a quick review. For a position time graph, the slope tells us what the velocity is. For a velocity time graph, the slope tells us what the acceleration is. Also, for a velocity time graph, if we take the area that's trapped by it, that tells us our change in distance. So those are three things we can tell from these two graphs. There's a third thing that we can, there's a fourth thing I should say that we can tell, and it's from an acceleration time graph. Let's just do a short demonstration here. Let's say our acceleration is 5 meters per second squared. That's the number. And let's say our time interval is 4 seconds. Because we're only dealing with horizontal lines on this graph, then the slope's not going to tell us a whole lot. But the area trapped by it is going to tell us a good amount. So just to kind of think about what this area is going to tell us, let's think about what would happen to the units. Obviously, base times height, 4 times 5, that's equal to 20. But what does that 20 actually mean? Well, the units on acceleration are meters per second squared. The units on time are seconds. So what unit results from this? That cancels with the square, meters per second. So the area trapped by an acceleration time graph tells us our overall change in velocity from beginning to end. So from this graph, I can tell that I've gained 20 meters per second. I'm going 20 meters per second faster here than I was in the beginning. That's what this area tells us. And that's also on your formula sheet too. So, questions on this so far? Okay. So yeah, the slope of a velocity time graph tells you acceleration. The area trapped by this graph tells you change in velocity. And when we think about acceleration, it's kind of an interesting thing because it's opposite the direction you would think it would be. Like when you're getting on the highway and picking up speed, what direction do you feel pushed? Well,
I guess back.
backward, yeah. You're picking up speed and you kind of feel like you're pushed to the back of your seat. So it feels like it's a backward force. But that's actually a forward force because that's your car pushing you forward.
That's what I was thinking.
Yeah, the sensation of you going back is just your body's response to that force.
I was thinking about it in the car today. Like,
Good.
if you're, like, if you could just, like, see yourself, like, you would just be sitting, but you're not moving.
Mm-hmm.
But the car is moving, isn't it? You're just like,
It's weird, isn't it?
Is the car moving and then it just, like, I don't know, that's a stupid question. Never mind.
I'm sure it's not a stupid question.
It sounds stupid. It's like, so we're in one position, and the car's moving forward, so is that, like, the car almost, like, moving us, or just physically go backwards?
Yeah, I mean, it's Newton's first law. You know, you want to stay at whatever velocity your body was at before you get on the highway. So when your car is picking up speed, your body's like, hey, I want to stay at the old speed. And so you feel that force.
So that's basically the car, like, moving you?
Yeah,
Oh, okay.
it is. It is. It's the car meeting you. And like when you're exiting the highway, it's kind of like you meeting your seatbelt. Because you're slowing down, so you know there's a force going backwards, but you feel like you're pushed forwards. Because again, that's your body's response to that change in velocity from Newton's first law.
So people, like, back in the old days when they didn't have seatbelts,
Basically, yeah, you'd have to stop yourself. Yep.
Like a go-kart,
I
or
mean,
Yeah.
everyone.
you know, like when you're in a go-kart, or a go-kart, no, not a go-kart. A golf? Oh, okay, there you
Oh,
go.
golf cart, sure. Yeah.
I'm saying go-kart, and I was like,
So, and the same thing is true. Well, let me just kind of show you. If you're ever wondering what direction your acceleration is in the same direction as your force. So, I guess I'll do this back here for the sake of the folks at home. So, I got my cup of water filled pretty much to the brim here. Now, if I go forward towards the door, my overall force, my overall acceleration is directed that way. Of course, what direction is the water going to fall? Backwards, yeah. Now my hand and my floor get all wet. And if I'm about to come to a stop, yeah, it goes forward. So one way to think about acceleration is just think about yourself holding a cup. Whatever direction the water goes is the opposite the direction of your acceleration. Opposite the direction of your force. Yes?
Can you use like bubbles as an example with the bubble line? So like, you know, like, so you like fill it up and then it goes up, but if you stop it goes like that and it'll pop.
Say that again? No, that's okay.
So like a bubble line.
The thing where you, and you make bubbles like that, right? Yeah.
So like if you start running, the bubbles will go up that way, but when you stop, it will break the bubble.
Oh, sure, yeah. Yeah, absolutely. Because when you change that speed, it puts a force on that bubble, which causes it to pop. That's exactly right. Yeah. Sure. I'll get you a pass. The other thing to take note of is that this also happens when you are moving in a circle. If you go in a circle in your car, you feel pushed to the edge. Just like, I'm going to have to move this away from the camera. If I go in a circle with my water here, the water goes out. So what does that mean about the actual force? Nope. In, yeah. Because the force and the acceleration is always opposite the direction that the water's going to go. So in this case, water's going out, so the force is in. Okay. Time to do a little bit of practice here. These last 15 minutes of our week.
They just posted the basketball game.
Oh, did they?
Sign up.
Oh, the sign up?
Oh.
So you're going to want to make 3 more graphs. We're going to be doing a lot of practice here. So if you have some extra time, go ahead and draw, I don't know, maybe 3 more sets of these 3 graphs. And we'll see if we can start to get an understanding of this. So let's take another scenario here. Let's say that the shark, instead of picking up speed from the origin, we'll say that he has started out. Thank you. Sorry. He has started out with a pretty large velocity. So in this case, time begins right now. Time stops. So he starts out with a fast speed, but then he slows down. And let's see if we can figure out how to put that on our position, velocity, and acceleration time graphs. So, we knew he began at the origin, so he's going to start here. But he starts with a large speed, a large velocity. So the question is, what is that going to look like on a position time graph? Well, the bigger the speed you have, the bigger the slope you're going to have right here. So we're going to start out with a large slope. Now as time goes on, the shark slows down. And so that means the velocity slows down, and therefore the slope will get smaller and smaller. So that scenario would look something like this. So again, you have to make sure you're aware that the slope on this graph represents velocity. So if shark begins with a fast speed and then starts to slow down, that means we're going to start with a big velocity because that corresponds to the big slope. And then as time goes on and that shark slows down, that means our velocity and therefore our slope will get smaller and smaller and smaller. In terms of the velocity time graph over here, well, we know we start with a large velocity. Is that large velocity positive or negative? It's going to be positive because we are moving away from the origin. Anytime you're moving away from the origin, it's going to be a positive value. So we start with a large positive velocity, and as time goes on, the shark slows down, ultimately reaching a velocity of 0. So that means the velocity is going to get smaller and smaller, ultimately reaching 0. Now the acceleration time graph is going to be the easiest one to draw. Is this a positive, negative, or 0 acceleration? Negative, because we've got ourselves a negative slope here. So on a velocity time graph, the slope tells us about acceleration. Because this is a negative slope, we have ourselves a negative acceleration.
So negative slope equals negative acceleration.
Yes. Let's try another scenario where the shark is changing speed. Let's say that time begins. He starts away from the origin here, and we'll say that time begins right now. Time stops. So he started out really, really slow, maybe even at rest. As time went on, he picked up speed, and he went faster and faster and faster, ultimately reaching the 0 point, the origin. So let's see if we can figure out what's going on there on our graphs. So if he began away from the origin, that means we're going to start somewhere up here on our position time graph. Because that's away from the 0 point. So the question is now, where do we go from here? Well, we started with a velocity of nothing. So that means we're going to start with a slope of nothing. Because the slope on this graph represents velocity. As time went on, though, the shark had an ever-increasing velocity. And because he was going towards the origin, that's a velocity in the negative direction. So what that means is that our slope is going to grow in the negative direction because his velocity is growing in the negative direction. So it would look something like this. So we start with a slope of about 0 because we start with a velocity of 0. As time goes on, the shark started going faster and faster in the negative direction. So our slope gets bigger and bigger in the negative direction. In terms of the velocity time graph, we start with a velocity of 0, which means we're going to begin right here. As time goes on, our slope gets bigger and bigger in the negative direction. So our velocity is growing in the negative direction, which means that our velocity is going to go like that. It's getting bigger and bigger as time goes on in the negative direction. Does this velocity time graph correspond to a positive or negative acceleration? Negative, because it is a negative slope. The slope on a velocity time graph represents acceleration. So because the slope is negative, the acceleration is negative. Questions on this one? Okay. Yes?
It's not really on like this problem, but for like the acceleration, does it matter how far you can go from the origin if it's negative or positive?
Yeah. I mean, if this is a really, really steep slope going like this, then I would make this more negative. If it was very shallow, smaller slope, we'd have a smaller acceleration. All right, let's do the one scenario that we haven't done yet. All right, so now the shark starts over here again, and he is going to, this time, pick up, he's going to be slowing down. He's going to be slowing down as he approaches the origin. So he's going to start with a large velocity, then he slows down, ultimately reaching 0 when he gets to this point. So he starts back here, really, really big velocity, but then he slows down. So let's see what that's going to look like on our graphs. He does begin away from the origin, which means he'll start up here somewhere. And he begins with a large velocity. Is it a large positive or negative velocity? Negative, exactly, because he's going towards the origin. So because he's starting with a big negative velocity, that means our graph is going to start with a big negative slope. So it's going to start by going down very sharply. Now, as time goes on, the shark slowed down. So what that means is that our slope here is going to get less and less. So here it's a very big negative slope, and because slope represents velocity, as time goes on, that slope is going to even out because the velocity gets smaller and smaller. So maybe it would look something like this. So once again, we begin with a big negative slope because the shark began with a big negative velocity. As time went on, the shark's velocity decreased, which is why our slope is decreasing, ultimately reaching a slope of 0 because the shark ended at rest. For the velocity time graph, we begin with a big negative slope over here, which means we started with a big negative velocity. Therefore, we're going to start way down here in big negative velocity territory. As time goes on, you can see our slope decreases, ultimately reaching 0, which means our velocity will decrease, ultimately reaching 0. Maybe something like that. And what is our acceleration going to be here? Positive, negative, or neither? Positive, because we've got ourselves a positive slope right there. It's all about the slopes when you're making these graphs, folks. You have to realize that the slope on this graph tells you about velocity, and the slope on this graph tells you about acceleration. Once you can internalize that, you'll be able to draw these graphs without any effort at all. Those are the main scenarios here. And I think that's probably where we can end. Yes?
I think you said it was negative.
What's negative? Not in this case. The acceleration is going to be positive here because we've got a positive slope on our velocity time graph. The last example, I think it was negative.
Didn't you say it was coming towards it?
Yeah, it's headed in the negative direction. It's got a negative velocity, because this is below the 0 point. But this is that funky scenario where we are slowing down in the negative direction. So it's kind of like having two negatives and having them make a positive.
Oh, so if you slow down in the negative, that makes it a positive.
Yeah. So, real quick, this will be the last thing I say. That brings up a really good point. I'm glad I can add this in. you can think about acceleration as the positive and the negative direction and picking up speed and slowing down. So let's say we are speeding up, going away from the origin. So going away from the origin is the positive direction. Picking up speed would be a positive thing too. So two positives make a positive. That would give you a positive acceleration. That's not this case, I'm just saying. Now let's say you are moving in the positive direction away from the origin, but you're slowing down. Positive and a negative make a negative. So in that case, you would have a negative acceleration. Now let's say you are moving toward the origin, so that's the negative direction, but you're speeding up. So that would be positive. And a positive and a negative make a negative. So under those conditions, you would also have a negative acceleration, picking up speed in the negative direction. And finally, that last one, let's say you are going in the negative direction toward the origin, but you're slowing down. That's another negative. Two negatives make a positive. And so under those conditions is what we see here. That's why we have ourselves a positive acceleration. So that's just another way to think about it. Personally, I just think about the slopes, and that's easier for me. But you can always check your work that way too.